In modified superfluid vacuum theory, the universe is filled with an invisible, frictionless quantum fluid, but it isn't an infinitely smooth liquid. If we zoom all the way down to the absolute limit of physical reality, the Planck scale, we find a hyperdense, granular lattice of ultra-fine components. Space has a physical grain. When we look at empty space, our eyes tell us there is nothing there. Mainstream physics treats the vacuum as a void, an abstract mathematical backdrop where things happen. But what if space isn't empty at all? What if it is a physical, material substance? To understand how this quantum fluid creates physical reality, we trace a 5-tier scaling hierarchy from the subplanck realm to observable matter. At tier 0, we have etherons, the ultimate continuous fluid particles of the vacuum. At tier 1, coherent etheron circulation forms torans, fundamental, Planck-sized vortex rings. At tier 2, these torans assemble along 20 triangular faces and 12 vertices into icosahedral cages called microcells. This regular, quasicrystalline packing forms the quiet, resting spatial grid. Why icosahedral geometry? Because parallel vortex stacking causes severe fluid friction and turbulence. The icosahedron's 5-fold golden ratio symmetry allows adjacent torans to feed return flows into one another seamlessly, creating a stable, self-contained ground state. At tier 3, when phase excitations pass through adjacent microcells, their phase funnels interlock along continuous channels. This forms vortex filaments, physical, three-dimensional strings woven out of phase-locked microcells. Unlike standard string theory, which relies on abstract zero-thickness lines vibrating in unobserved extra dimensions, MSVD filaments are three-dimensional fluid tubes embedded in physical space. Their vibrational modes, specifically circularly polarized Kelvin waves, give rise to the quantized properties of energy. At tier 4, we reach matter itself, the soliton. In MSVT, elementary particles are not solid objects placed into space. They are localized, self-sustaining topological knots trapped within the spatial grid. Mass is simply the localized rotational momentum density of the vortex knot, creating a surrounding pressure gradient in the grid. Charge corresponds to the chirality and direction of fluid flux exiting the cell. When positive and negative torin flows nest in equal, counter-rotating balance, external flux cancels completely, giving rise to neutral particles like the neutron while preserving dense internal mass. Matter and space are made of the same fluid medium. Forces are simply hydrodynamics in action. Electrostatic attraction occurs when adjacent nodes spin in phase alignment, creating a low-pressure Bernoulli suction channel between them. Repulsion occurs when opposing spins clash, creating shear turbulence and high dynamic stagnation pressure. At nuclear distances, the strong force manifests when adjacent icosahedral nodes physically lock face-to-face. Their internal fluid channels merge into a single shared vortex tube, cleanly explaining both asymptotic freedom at close range and color confinement when pulled apart. Finally, radiation and electromagnetism are the transverse shear waves of the lattice. A photon is a localized wave packet propagating across the packed microcell matrix, inducing a sequential chiral precession in each icosahedral frame as it passes. Light does not travel through a void. It is the traveling disturbance of the vacuum itself. Having established our 5-tier scaling hierarchy from etherons up to solitons, we now turn to the foundational ontology of modified superfluid vacuum theory. The historical trajectory of modern physics left a central question unanswered. What is the physical mechanism behind wave propagation in a vacuum? James Clerk Maxwell's formulation of electrodynamics inherently relied on a continuous, space-filling medium capable of storing elastic tension and rotational momentum. Similarly, Hendrik Lorenz's early relativity models presumed a fundamental baseline frame to govern the velocity of light. However, The early 20th century abandonment of the classical ether was largely driven by a rigid visualization of the vacuum. The prevailing mechanical models of that era viewed the background medium as a static, solid-like material through which celestial bodies plowed like objects moving through air. This crude model inevitably created conceptual conflicts that led mainstream physics to adopt an abstract geometry of empty space. To understand how a fluidic medium offers a distinct physical perspective, we must re-examine two milestone optical experiments: the Michelson-Morley experiment of 1887 and the Michelson-Gale-Pearson experiment of 1925. The Michelson-Morley experiment attempted to measure the Earth's linear translational velocity through a static ether wind as it orbited the Sun, yielding a null shift. In contrast, the 1925 Michelson-Gale-Pearson experiment measured the optical phase shift induced by the Earth's axial rotation, a direct manifestation of the rotational Sagnac effect. In modern physics, special relativity accounts for the Sagnac effect geometrically within rotating spacetime coordinates without requiring a physical medium. MSVT does not dispute this relativistic calculation. Rather, it provides a physical, hydrodynamic visualization for these kinematic behaviors. In a quantum superfluid, linear translation and rotation produce fundamentally different boundary conditions. First, linear translation. When a solid body moves linearly through a zero-viscosity superfluid, the fluid undergoes local hydrodynamic entrainment. This forms a localized boundary layer or protective frame that moves along with the body, masking any linear material wind and producing the null signature observed in the Michelson-Morley experiment. Second, axial rotation. Conversely, rotation introduces a topological constraint. A superfluid cannot rotate as a uniform solid body. Instead, rotational energy enters the substrate by generating localized vortex alignments. Because this vorticity is topologically tied to the system's angular momentum, it cannot be fully masked by a local boundary layer. The measurable phase shift observed in Michelson-Gale-Pearson is thus interpreted in MSVT as a physical manifestation of the substrate's rotational inertia. Modified superfluid vacuum theory formalizes this intuition. Space is not an empty, abstract extension of coordinates, but an ultradense, non-baryonic quantum fluid substrate operating at a fundamental Planck scale carrier frequency, designated as F0, approximately equal to 2.95 times 10 to the power of 42 Hz. Rather than treating this high-frequency oscillation as an emergent byproduct derived from lower energy inputs, MSVT postulates that the primary vacuum substrate possesses an intrinsic zero-point breathing cycle operating at the Planck scale limit. The carrier frequency, F0, equals the speed of light divided by 2 pi times the Planck length, yielding approximately 2.95 times 10 to the power of 42 Hz. When accounting for 4 valent graph routing topologies incorporating a 4-pi spherical double-cover phase geometry, the effective angular clock speed scales to f4 pi, approximately equal to 7.42 times 10 to the power of 42 Hz, while 2.95 times 10 to the power of 42 Hz serves as the primary cyclic carrier frequency, f0. By viewing the vacuum as a dynamic, quantized superfluid oscillating at this universal clock speed, we preserve the mathematical successes of relativity while restoring a physical, wave-propagating medium to the universe. To construct an internally consistent alternative to the abstract geometric coordinates of standard spacetime models, MSVT operationalizes the vacuum as a physical, quantized cellular substrate. Rather than existing as a featureless void, space is defined as a non-baryonic matrix of Planck scale coordinate vertices, referred to as the spatial graph, G, composed of vertices V and edges E. The universal physical parameters that dictate macroscopic wave propagation, specifically the vacuum permittivity, epsilon0, and vacuum permeability, mu0, are defined as the fundamental mechanical constraints of this underlying fluidic matrix. First, permittivity, epsilon0, is defined as the spatial phase elasticity or volumetric bulk compliance of the graph network. It represents the local volume restoring compliance of the vacuum medium when its background breathing phase undergoes compression or dilation. Second, permeability, μ0, is defined as the spatial rotational inertia density of the substrate, quantifying the medium's resistance to local torsional deformation and angular displacement. The speed of light, c, is therefore locked as the acoustic wave velocity of transverse longitudinal modes propagating through this elastic inertial medium. The speed of light, c, equals 1 divided by the square root of permittivity times permeability, which equals the square root of the bulk modulus K0 divided by the density ρ0, where K0, representing 1 over epsilon 0, is the bulk modulus of the background medium, and ρ0, representing μ0, is its effective inertial mass density. To regulate the ultraviolet divergence of quantum field calculations without introducing arbitrary renormalizations, the spatial graph is characterized by a fundamental, invariant lattice spacing, the Planck length, L Planck, and a primary background carrier frequency, f0. Rather than treating the approximately 10 to the power of 42 Hz oscillation as an emergent byproduct derived from lower energy electromagnetic inputs, MSVD postulates that the primary vacuum substrate possesses an intrinsic zero-point breathing cycle operating at the Planck scale limit. The fundamental carrier frequency, f0, equals the speed of light divided by 2 pi times the Planck length, yielding approximately 2.95 times 10 to the power of 42 Hz. As noted, in 4-valent graph routing topologies incorporating a 4-pi spherical double-cover phase geometry, the effective angular clock speed scales to f4 pi, approximately equal to 7.42 times 10 to the power of 42 Hz, while 2.95 times 10 to the power of 42 Hz serves as the primary cyclic carrier frequency, f0. This baseline oscillation rate establishes the fundamental clock speed of the spatial hardware. The unexcited background vacuum is not a passive emptiness, but an active, hyperdense fluid medium oscillating uniformly at f0. Macroscopic energy transitions, subatomic particle rest masses, and laboratory electromagnetic wave frequencies represent low-frequency subharmonic modulations, delta f much less than f0, layered on top of this fundamental carrier wave. Rather than treating electrostatic, magnetic, and gravitational forces as distinct fields mediated by hypothetical virtual particles, MSVD investigates whether macroscopic field vectors can be mapped to the fundamental geometric degrees of freedom of a compressible, elastic superfluid substrate in the linearized acoustic limit, where delta rho is much less than ρ0. By analyzing the background medium through continuum wave dynamics, 3 macroscopic field manifestations are structurally mapped. First, longitudinal phase displacements correspond to the electric field vector, E. Second, transverse rotational vorticity corresponds to the magnetic flux density, B. Third, isotropic density and tension deficits correspond to the gravitational pressure gradient, grad P. To understand the electrostatic field and phase scattering, an elementary electric charge in MSVD is modeled as a localized topological phase defect embedded within the f0, approximately 2.95 times 10 to the power of 42 Hz, 0-point breathing lattice. We define the local phase deviation of a medium as a scalar field, phi of x and t. The measurable electric field vector, E, corresponds to the negative spatial gradient of this phase displacement, E equals negative grad phi. When 0-point lattice phonons scatter off these localized topological phase defects, the resulting acoustic radiation momentum flux propagates isotropically through the 3-dimensional grid. Integrating this wave momentum flux across a closed spherical boundary, A, yields Gauss's law identically. The closed surface integral of E dot d equals the charge, E, divided by vacuum permittivity, epsilon 0. Because the 3-dimensional surface area of a sphere scales as 4 pi r squared, the isotropic flux naturally reproduces the inverse squared distance dependence, 1 over r squared, of Coulomb's law. Regarding the charge sign mechanism, in standard continuum acoustics, pulsating volume monopoles in an infinite fluid obey the secondary Bjerknes force, where the average force equals negative ρ0 divided by 4 pi d squared times the time average of the derivative of volume 1 times the derivative of volume 2. For linear acoustic monopoles, in-phase pulsations yield an attractive force, while out-of-phase pulsations yield a repulsive force. A naive application of linear acoustic monopole dynamics therefore predicts the exact opposite sign behavior required by Coulomb's law, where like charges repel and opposite charges attract. To reconcile this sign discrepancy without introducing arbitrary curve fits, MSVT treats charge-sign interaction as an open working hypothesis. In a discrete quantum lattice with nonlinear dispersion, phase defects scatter zero-point phonons, such that in-phase interference, delta phi equals 0, generates an effective radiation pressure buildup between defects, resulting in repulsion. Out-of-phase interference, delta phi equals pi, yields a local pressure drop, resulting in attraction. Several candidate mechanisms, including acoustic volume pulsations, V-squared Bernoulli suction, and ideal vortex kinetic energy overlap, have been rigorously stress-tested and shown to fail Coulomb's sign or scaling mechanics. Whether a nonlinear discrete lattice momentum tensor can invert the classical Bjerknes sign remains an active, open theoretical question. Moving to the magnetic field as transverse rotational vorticity, because the spatial graph network functions as a hydroelastic medium, a directional phase displacement undergoing physical translation through the substrate introduces localized shear. This shearing torque forces the non-viscous background fluid into rotational motion, generating vortex lines or loops. We define the magnetic flux density vector, B, as the physical vorticity or curl of the underlying fluid velocity field, V, B equal curl V. Because magnetic fields represent rotational vorticity, they satisfy the vector identity. Divergence of B identically equals the divergence of curl V, which equals 0. This provides a direct mechanical explanation for the absence of magnetic monopoles. A vortex filament cannot terminate abruptly in the interior of a fluid. It must form a closed loop or extend to a boundary. The vacuum permeability, mu0 equals ρ0, measures the rotational inertia of the medium, locking the transverse shear speed to the longitudinal phase speed via C equals 1 divided by the square root of epsilon 0 times mu0. Finally, for gravity as a second-order isotropic link tension deficit, while electricity and magnetism represent first-order directional phase and shear modulations of the background carrier wave, gravity operates as a second-order, long-wavelength acoustic density deficit. When mass energy is localized within the medium as a stable subatomic wave packet or topological defect, it sequesters a fraction of the local lattice processing bandwidth. This localized energy concentration creates a subtle, isotropic depletion in the surrounding zero-point lattice density, ρ0, and bulk compliance, epsilon 0. Because the background node density drops near a mass concentration, the local acoustic wave velocity, C of R, decreases slightly. C of R equals the square root of K0 over divided by ρ0 of R. This spatial gradient in wave velocity manifests macroscopically as gravitational time dilation, light bending, and an attractive pressure gradient, grad P, directed toward the central mass. To establish a scale-invariant mechanics of the primary vacuum, MSVT connects directly to the established literature of hydrodynamic analog gravity and superfluid vacuum models. The concept that Maxwellian electrodynamics and gauge fields can emerge from fluid dynamics has a rich academic lineage. First, Marmanis in 1998 formalized the mathematical correspondence between Euler-Navier-Stokes' fluid vorticity and Maxwell's field equations. Second, Cam demonstrated that acoustic wave propagation in a compressible fluid obeys an action principle isomorphic to classical electrodynamics. Third, Volovic in 2003 established in the universe in a helium droplet that low-energy excitations in a quantum Bose-Einstein condensate naturally exhibit Lorentz invariance, analog gravity, and topological defect quantization. Building on this lineage, recent phenomenological models, such as the vacuum unified solitonic condensate theory by Khalid and Golubowski in 2026, provide a useful continuous macroscopic baseline. By modeling the vacuum substrate as a continuous, compressible quantum condensate governed by the nonlinear Grospadevsky energy functional, such models demonstrate how electromagnetic wave speeds and topological defects can be framed within fluid mechanics. In this continuous paradigm, the baseline wave speed of the medium is derived from the Bogoliubov dispersion relation of the condensate. Omega squared of k equals c sub s squared times k squared, plus h bar squared times k to the fourth power, divided by 4 times m effective squared. In the long wavelength acoustic regime, where k times 11 is much less than 1, and 11 represents the healing length, higher-order dispersion terms vanish, locking linear wave propagation to the acoustic sound speed, c sub s, which equals the square root of bulk modulus k0 divided by density, ρ0. Light is conceptualized as a linear acoustic shear and phase excitation in the substrate, establishing the speed limit, c, as the acoustic Mach barrier of the primary medium. Furthermore, elementary particles can be modeled as localized topological fluid excitations. Under the Kelvin circulation theorem, where circulation gamma equals the closed line integral of v.dr, which equals n times kappa, circulation quantization provides a hydrodynamic analog for charge conservation. Localized vortex loops illustrate how rest mass energy can be stored in compact fluid geometries. However, as we demonstrate in Chapter 5, extrapolating this smooth continuum down to Planck dimensions encounters fundamental structural fracture points. While smooth fluid models offer valuable macroscopic analogies, continuous field calculus eventually encounters severe structural limitations when extrapolated down to the Planck scale. These limitations are not errors in execution. They're the unavoidable mathematical artifacts of applying continuous, infinitely differentiable calculus across real, three-dimensional space to a discrete, pixelated spatial hardware. Standard continuous fluid models exhibit 4 major structural fracture points when evaluated at the ultraviolet boundary. First, the core divergence problem. When evaluating the integrated energy of a compact, multi-strand topological vortex, not down to an infinitesimal point, where approaches zero, the local bending energy integral yields a logarithmic divergence. The core stiffness coefficient, C core, equals 4 pi times the integral from 0 to infinity of 1 over rho times the derivative of f with respect to rho squared, plus rho times f squared times 1 minus f squared, d rho, which is proportional to the natural logarithm of rho max. Because continuous differential calculus presumes infinite spatial subdivisibility down to or equals 0, smooth field integrations overestimate the localized core curvature energy of subatomic particles, requiring artificial mathematical cutoff parameters to match real-world observations. Second, the spin vector cancellation. In a smooth continuum, evaluating particle spin via a continuous hydrodynamic cross-helicity integral, where helicity h equals the volume integral of velocity dot vorticity d3x, ties spin directly to the signs of the fluid's phase twists. When integrating over composite multi-strand configurations, such as a proton composed of fractional charge windings, opposing twist signs cause an exact algebraic cancellation. The calculated helicity of the proton identically equals 0. Smooth macroscopic fluid integrals fail to preserve quantized half-integer spin, h bar over 2, demonstrating that spin cannot arise from continuous vector velocity fields alone. Third, the electrogravitational ratio overshoot. When continuous models derive gravity as a second-order fluid pressure deficit, where gravitational force is proportional to negative grad p, integrating smooth fluid pressures across an unbroken spatial continuum overshoots the empirical electrogravitational force ratio, 10 to the power of 36, by roughly 2 orders of magnitude, predicting 10 to the power of 38. This occurs because smooth calculus fails to account for the geometric node dropout that occurs across a discrete spatial grid. Fourth, unbounded family generations. Because a continuous fluid field possesses infinite geometric freedom, smooth field models provide no architectural barrier to bound particle repetitions, leaving the origin of exactly three particle generations: electron, muon, and tau, underived. In summary, transitioning from smooth continuum calculus to the discrete spatial graph network in MSVT does not discard classical fluid insights. It provides the explicit, pixelated hardware required to regularize these divergences. To resolve the ultraviolet divergences inherent in continuous field calculus, MSVT replaces smooth spatial coordinates with a directed, regular cellular graph, G, composed of vertices V and edges E. The vertex set V represents quantized spatial nodes separated by an invariant minimum Planck metric, where distance between nodes I and J is greater than or equal to L Planck, while E represents link channels routing phase information at the foundational lattice frequency, F0, approximately equal to 2.95 times 10 to the power of 42 Hz. Under this discrete geometry, the state space is defined over L2 of V, with a complex local state, psi sub I, equals the square root of rho sub I times e to the I phi sub I, indexed across individual nodes I and V. The continuous gradient operator is replaced by the discrete graph exterior derivative, D, mapping L2 of V to L2 of E, acting along a link E connecting nodes I and J as d psi along link E equals psi sub j minus psi sub I. Correspondingly, the spatial Laplacian operator is replaced by the graph Laplacian operator, delta graph, equal to d star d, acting on node I as delta graph psi at node I equals the sum over all adjacent nodes j of psi sub I minus psi sub j, where j adjacent to I represents the set of neighboring nodes bound by the coordinate valence degree of I, equal to n sub v, which equals 4. This mathematical structure regularizes the core divergence problem. In smooth fluid models, integrating the curvature energy of a compact topological vortex down to or approaching zero produces an infinite logarithmic blowup. In MSVT, core integration is projected through the discrete UV cutoff operator, lambda hat graph. The infinite continuous integral is converted into a discrete summation over integer-spaced concentric topological node shells, indexed by integer m. The discrete core stiffness coefficient, C core discrete, equals 4 pi times the sum from shell m equals 1 to mir of 1 over m times delta mf squared, plus m times f sub m squared times 1 minus f sub m squared. At the central core node, where m equals 0, destructive phase interference depletes local density, setting F0 equal to 0. At the first adjacent spatial node shell, where m equals 1, the discrete boundary truncates the phase transition at a finite value, F1, approximately equal to 0.583. Because the shell index m is restricted to integer steps greater than or equal to 1, the denominator cannot evaluate to 0, forcing the calculated core energy to saturate naturally at the boundary of the primary Planck pixel. The curvature energy in MSVT equals lambda hat graph applied to 4 pi squared c sub f times m Planck c squared, which identically equals 4 pi squared c sub f divided by n sub v times L Planck times m Planck c squared. The 64-fold energy overshoot seen in unregularized continuum models vanishes because the physical network hardware cannot process gradients smaller than the single node link itself. In standard relativity, the speed of light, c, is an axiomatic postulate. In the discrete graph of MSVT, c represents the universal data routing latency of the spatial hardware. Because space is constructed from discrete nodes operating at a universal carrier frequency, F0, approximately 2.95 times 10 to the power of 42 Hz, a phase excitation cannot transition across space instantaneously. Every spatial step requires a discrete, sequential node switching cycle. Processing latency equals change in nodes divided by change in clock cycles, which defines the speed of light c. When a localized wave packet accelerates through the grid, its constituent pathways process directional spatial hops and internal phase updates simultaneously. As directional hops approach the maximum bandwidth of one node per one clock cycle, available processing cycles for internal updates decrease, providing an intuitive mechanical analog for relativistic time dilation and mass energy scaling. Next, regarding the resolution of the spin vector cancellation in a smooth fluid, evaluating baryon spin via a continuous cross-helicity integral. Helicity H equals the volume integral of velocity dot vorticity, d3x, causes an exact algebraic cancellation, yielding zero helicity due to opposing charge winding parameters. MSVT decouples particle spin from continuous fluid velocity vectors. Drawing on concepts from loop quantum gravity spin networks and braid group topology, quantum spin is modeled as the discrete topological permutation symmetry of lattice pathways, p-hat path, as they route through coordinate nodes. When a multi-strand braided graph defect undergoes a 2π spatial rotation, directional links executing exchange operations within the non-abelian braid group, B3, introduce a global phase sign inversion, turning psi into negative psi. A full 4π rotation is required to restore the original network connectivity matrix, turning psi back into positive psi. Because this permutation symmetry depends on the topological connectivity of the graph pathways rather than continuous vector signs, composite defects natively preserve quantized half-integer spin, where spin s equals h bar over 2. In MSVT, fractional electric charges, plus 2/3 and minus 1/3, are modeled as phase flux partitions across a fixed node valence, degree of I equals n sub v, which equals 4. With 3 spatial channels routing outward and 1 internal clock link, any incoming quantized phase flux, phi 0, entering a node coordinate is partitioned into fundamental thirds, 1/3, by the routing geometry of the lattice pixels. To model why the standard model contains 3 generations of elementary leptons, electron, muon, and tau, and quarks, MSVT introduces the fractional graph Den twist operator, t-hat graph. A Den twist executes a discrete topological transformation that shifts routing paths by a fractional phase angle map to the node valence, 2π divided by n sub v. T-hat graph acting on psi sub I equals e to the power of I times 2π over n sub v times j graph, all multiplied by psi sub I, where j graph is the discrete angular momentum routing tensor. Generation 1, the electron, represents a single-loop path twist, t-hat graph, to the power of 1. Generation 2, the muon, represents a double-loop path twist, t-hat graph squared, packing higher link tension into the local footprint. Generation 3, the tau, represents a triple-loop path twist, t-hat graph cubed, reaching maximum channel density. We propose a link capacity hypothesis on a 4-valent lattice junction. Let the maximum structural routing capacity, Cmax, of a localized spatial junction be bounded by the available pairwise link connections sharing a coordinate boundary. Cmax equals n sub v times degree of I, which equals 4 times 4, yielding 16 available channels. If each successive Den twist iteration, t-hat graph, to the power of n, requires a channel allocation scaling as capacity used for tier n equals n squared plus n sub v to maintain path separation without crosstalk. First, generation 1, where n equals 1, requires 1 squared plus 4 equal to 5 channels used out of 16 available, leaving 11 channels remaining. This tier is stable. Second, generation 2, where n equals 2, requires 2 squared plus 4 equal to 8 channels used out of 16 available, leaving 8 channels remaining. This tier is stable. Third, generation 3, where n equals 3, requires 3 squared plus 4 equal to 13 channels used out of 16 available, leaving 3 channels remaining. This tier is stable. Notice that the remaining 3 channels are less than the base node valence of n sub v equals 4 required to frame a 4th layer. Fourth, generation 4, where n equals 4 requires 4 squared plus 4 equal to 20 channels. Because 20 is greater than 16, channel requirements exceed the physical spatial junction capacity. A fourth generation is geometrically prohibited by the network hardware, proving that particle family generations naturally saturate at exactly n generation equals 3. The cosmological constant paradox, frequently termed the vacuum catastrophe, arises when quantum field theory calculates the zero-point energy density of the vacuum down to the Planck length, yielding a theoretical baseline density of approximately 10 to the power of 111 joules per cubic meter. Conversely, astronomical observations of cosmic acceleration restrict the effective cosmological constant, lambda effective, to approximately 10 to the power of minus 9 joules per cubic meter. This overestimates the observed energy density by 120 orders of magnitude. Within MSVT, this discrepancy is addressed by applying a foundational distinction from fluid hydrodynamics, the operational separation of absolute background pressure from differential gradient pressure. In standard fluid mechanics, a submerged body does not experience net translational acceleration from the isotropic background pressure of a surrounding fluid. It reacts exclusively to pressure gradients, grad P, acting unevenly across its boundary. If a medium is uniform and isotropic, an immense background pressure exerts zero net shear, or macroscopic directional force. To formalize this, MSVT separates the vacuum energy stress state, rho total, into two distinct mathematical components. Rho total equals rho baseline plus lambda effective, where rho baseline, approximately equal to 10 to the power of 111 joules per cubic meter, represents the absolute invariant isotropic energy density of the F0, approximately 2.95 times 10 to the power of 42 Hz, 0-point lattice. Because it is uniform across the spatial graph, its net spatial pressure gradient is 0, grad P baseline equals 0, exerting no direct gravitational acceleration on localized wave packets. Lambda effective represents the effective cosmological constant, modeled as the residual volumetric phase relaxation generated by the cosmic scale expansion of the spatial graph fabric over time. We model the long-term phase relaxation of a lattice as a dimensional scaling ratio between the minimum Planck clock cycle, tau p, and the age of the cosmic graph, tau cosmic. Lambda effective is approximately equal to rho baseline times the square of tau p divided by tau cosmic. Evaluating this expression with standard parameters. First, absolute baseline density, rho baseline, equals 4.6 times 10 to the power of 111 joules per cubic meter. Second, the Planck time constant, tau p, equals 1 divided by 2 pi f0, which equals approximately 5.39 times 10 to the power of minus 44 seconds. Third, the age of the expanding cosmic graph, tau cosmic, equals approximately 13.8 billion years, or 4.35 times 10 to the power of 17 seconds. Multiplying 4.6 times 10 to the power of 111 by the square of 5.39 times 10 to the power of minus 44 divided by 4.35 times 10 to the power of 17 yields lambda effective approximately equal to 7.05 times 10 to the power of minus 11 joules per cubic meter. This dimensional scaling ratio bridges the 120 order of magnitude gap, yielding an effective expansion density that aligns with observational cosmological data, 10 to the power of minus 9 to 10 to the power of minus 11 joules per cubic meter. While Chapter 9 addresses cosmic pressure, the final macroscale challenge is explaining why gravity is roughly 36 orders of magnitude weaker than electromagnetism, and fixing the 100-fold overestimation that occurs in continuous fluid models. As established in Chapter 5, when continuous fluid models derive gravity as a second-order hydrodynamic pressure deficit, where gravitational force is proportional to negative grad P, smooth integration across continuous space predicts a force ratio, scaling as m Planck over m proton squared, yielding approximately 1.69 times 10 to the power of 38. However, laboratory measurements yield an empirical force ratio of approximately 1.24 times 10 to the power of 36. Smooth continuum calculus overshoots the observed hierarchy by a factor of roughly 100, 10 to the 38 versus 10 to the 36. This occurs because smooth calculus integrates non-existent pathways between spatial coordinates, failing to account for the discrete geometric dropout across pixelated space. In MSVT, this continuum discrepancy is regularized by evaluating spatial flux through a discrete path connectivity matrix, C-graph, on a regular graph lattice where degree of I equals n sub v, which equals 4. A first-order electromagnetic phase mode propagates across direct, single-step link channels. Conversely, second-order gravitational link tension routes across the network as a pairwise joint correlation between adjacent path states. When calculating this correlation on a 4-valent lattice, the discrete geometric dropout factor, chi-graph, evaluates to 1 divided by n sub v times pi squared, which equals 1 divided by 4 pi squared, or approximately 0.02533. Applying this discrete network regulator to the raw continuum ratio, the ratio of electromagnetic force to gravitational force in MSVT equals chi-graph times 1.69 times 10 to the power of 38, which equals 1 over 4 pi squared times 1.69 times 10 to the power of 38, yielding approximately 4.28 times 10 to the power of 36. By introducing the hardware path constraints of a discrete grid, the factor of 100 overestimation that fractures continuous fluid models is naturally absorbed by the lattice geometry. This calculation serves as an order of magnitude dimensional scaling argument, demonstrating how discrete spatial pixelation bridges the gap between continuum fluid estimates, 10 to the 38, and real-world force hierarchies, 10 to the 36. Finally, regarding the single vortex ground state, evaluating the total kinetic energy of an isolated vortex ring in a superfluid substrate shows that global energy minimization strictly selects integer topological winding numbers n phi equals 1 and n theta equals 1. This proves that an isolated single vortex ring natively forms an unknotted one-to-one toroidal ring as its rest mass ground state. While an isolated single vortex ring strictly minimizes its rest energy at a one-to-one integer winding ratio, we conjecture that when the vacuum substrate is driven into a space-filling network or standing acoustic lattice, collective cross-mode interactions favor self-similar scale transitions governed by the golden ratio. This mechanism avoids low-order rational phase resonances that would otherwise induce turbulent vortex line reconnection and energy dissipation, providing the foundational stability of a vacuum. To transition modified superfluid vacuum theory from a theoretical framework to an empirically testable physics model, MSVT delivers specific, quantitative predictions that distinguish its discrete fluid substrate from continuous general relativity and smooth quantum field theory. First, local violations of Lorentz invariance via magnetorotational Sagnac interferometry. Because the spatial lattice possesses a physical rotational inertia, mu0, and an intrinsic carrier frequency, f0, approximately 2.95 times 10 to the power of 42 Hz. A macroscopic physical body undergoing extreme rotational acceleration induces localized vortex alignments in the spatial grid. While linear translation is masked by superfluid boundary layer entrainment, high-speed axial rotation combined with intense orthogonal magnetic fields creates a localized anisotropy in the background acoustic wave speed, c. MSVT predicts a microscopic phase-dependent directional variation in light speed, delta c over c, on the order of v squared over c squared scale by the local magnetic vorticity density. This local violation of Lorentz invariance is detectable using a combined magnetorotational Sagnac interferometer, providing a direct optical test for the substrate's physical rotational inertia. Second, subharmonic lattice dispersion at ultra-high energies. Because the spatial graph possesses a fundamental pixel spacing at the Planck length, L Planck, high-energy gamma-ray photons approaching subplanck wavelengths experience nonlinear dispersion governed by the discrete graph Laplacian. MSVD predicts that ultra-high-energy cosmic rays will exhibit energy-dependent arrival time delays across cosmological distances, deviating cleanly from standard Lorentz invariant vacuum propagation. Third, saturation of subatomic particle generations. As derived from our discrete DIN twist link capacity model, 4 valent pixel junctions reach full routing saturation at tier n equals 3. MSVD predicts a strict, fundamental absence of a 4th generation of elementary leptons or quarks at higher collider energy thresholds. In summary, modified superfluid vacuum theory provides a unified physical model that operationalizes the vacuum as a non-baryonic, quantized cellular substrate oscillating at a fundamental carrier frequency of 2.95 times 10 to the power of 42 Hz. By replacing continuous differential field calculus with a discrete 4-valent spatial graph network, MSVD achieves 5 core resolutions. First, it eliminates ultraviolet core energy divergences by saturating vortex, bending energy at the primary Planck pixel boundary. Second, it protects quantized half-integer spin through discrete graph pathway permutations, resolving the spin cancellation paradox of smooth fluid models. Third, it bounds elementary particle generations to exactly 3 through fractional DIN twist channel capacities. Fourth, it resolves the cosmological constant paradox by distinguishing absolute background zero-point pressure from long-term volumetric phase relaxation over cosmic time. Fifth, it absorbs the 100-fold continuous overestimation of the electrogravitational force ratio via the hardware path constraints of the spatial graph matrix. By bridging Planck-scale discrete geometry to macroscopic particle hydrodynamics, MSVD restores intuitive physical mechanics, wave-propagating media, and finite calculations to fundamental physics.